All right, hey everybody, welcome back to Physics with Dr. T. In this week's walkthrough, we're going to be looking at vectors and Newton's first law. Now, I brought along with me a basketball, and I'd like to illustrate that at the moment, this basketball is doing a fine job of demonstrating for us Newton's first law. It is an object not in motion, there are forces acting on it, and they are all balanced, leading to no change in motion. And so, while we're letting this basketball continue demonstrating Newton's first law, let's talk about this week's PRELAB activity. Okay, so for your PRELAB activity, you're going to navigate to the PhET page either through your D2L link or by right-click with while holding Control on the link that's in the PRELAB document, and it'll take you to this location. So you just double click on 2D and here we are. As you see, much of this information is already mapped out in the PRELAB activity, so let's just kind of quickly go over it. This is over here your display palette, and you see you get sums, you can show values, you can show angles. We're going to turn that off for right now. I'm going to leave that to you to decide what you want to show, at least in the short term. And then down here you can display the components in whichever configuration you like, such as in the right triangle configuration as vector components parallel to the axes but at the same starting point. And this area right here projects over to the appropriate axis for the components. Down here you have three vectors, A, B, and C. You cannot use more than three vectors in this simulator. So the trick here is to make your vectors original by changing their lengths and their angle of direction. Down here you can change it over to polar coordinates, but I don't recommend you do that because we want to stick around in the X, Y, Z components, or in this case X and Y components. So we'll click it back here and say A, B, C. From here you simply grab and drag. I'd start at the beginning. They're all going to be about the same length, so you just grab and drag it around. You see it kind of jumps to different locations, so I'll just kind of go up right here. Maybe I'll bring B over here and stick it on the tip end of A. Grab it and drag it down. Let's be a little bit funky here. I'm just really wanting to exaggerate and use the space up. And then C, now this is where it gets tricky. You are making three vectors that add up to be 0. You're going to confirm this through your calculations after you've printed this out. We are making the equilibrant vector, if you will, but this is not the resultant vector. You are making a third vector that sums the remainder to 0. So you put that in this place like so, and you move it. Now you'll notice as I've been moving those vectors around, if I click on A, it changes and shows you the length or the magnitude, the angle of that vector, the AX and AY. Same thing for B, same thing for C. There's an example in your PRELAB that shows all three vectors highlighted simultaneously. That is a doctored photo. The information is valid, it's just modified, so you won't be able to show all three simultaneously. You'll need to somehow preserve the values of each of these vectors, at least their component information. So then you come over here and you turn on one of the three types that you like. You can choose whatever one of those three that you like. I'm just using this one for personal preference. And now I want to move this . So this is one way you could set them up, and let's see how it looks. Like so. Okay, so that's fine too. But now you can see each vector with its own components showing. Maybe we'll move this up a little bit more just for a little bit more space when you go to print this out. And this is what you're going to print out and put into, so maybe I'll do a print screen. I'll grab print screen and then I'll paste this into Word or into Paint or a Paint program, and then add on the information for the length of each of those components along the X and Y. Make sure you don't get those mixed up. And then that's what you print and make the calculations according to the information in your PRELAB guide. And that's pretty much it. Okay, so now that you've had some experience working with two-dimensional vectors, now let's go ahead and expand our understanding into adding vectors. And in this week's laboratory, you're going to use three different approaches to accomplish this. The first step we're going to use is using the graphical method. This is where you actually draw the vectors out on a two-dimensional grid and determine the resultant vector through that process. And the way that we do that is we start with our first vector, vector A, coming from the origins, most natural place to start, and we map it out according to its direction and its magnitude. Then, at the tip of that vector, you start drawing your second vector. And the best way to do that is to sketch in a little XY coordinate that is parallel to the two principal axes. Then you measure your angle relative to the positive x-axis, as we always do, and the length. Now, this is the part that I want to make sure that we're very clear about. When you add A and B, you get a resultant vector, a vector that is equivalent to the two of those vectors summed together. That's this red line. Now, that resultant vector would start at the origin and continue to the tip of B. That is your resultant vector. And as you see, I've put the arrow, the tip, at the end of B. Now, that is the mathematical approach. When you're thinking about this in comparison to your strings and forces on the force table, what your third and fourth vector respectively are going to be for part 1 and part 2 are actually your equilibrium vector, where the vector points in the opposite direction of your resultant, because we expect that the resultant vector and the equilibrium vector are equal and opposite and therefore cancel each other out completely, leading to no motion. Once you've drawn your angle on the grid on your space, you'll measure the magnitude by measuring the length, and if you scaled, you need to scale back down. And then the angle, which doesn't scale, so you just measure that angle, record those as your resultant quantities in your graphical method table. Next, you're going to use the same configuration and solve it using the trigonometric method. This is a bit more mathematically intense, but again, this allows you an opportunity to compare two different approaches to measuring the vectors that you set up on your force table. The way to do this is that you'll have your two vectors, and this may be upside down compared to what you see in this setup here, but the general configuration is what you want to pay attention to, which is to say the relationship of the angles and legs to each other in order to use these two laws. Here we have vectors A, B, and C, where they have internal angles that may or may not correspond to the actual vector's relative location. A is going along the horizontal x-axis. That's the first vector that we know. Your second vector may be pointing this way, making this an obtuse triangle. It may be pointing this way to make it an acute triangle. Either way, this mathematical method does work, and here's why. The law of cosines here, if you look at it closely, has a part that you might recognize. If we cover up this part right here, now you see we've got a Pythagorean theorem. But Pythagorean theorem only works for a right triangle. So there's a correction that's been added to this to make the law of cosines work for you. And so we imagine that right triangle, this is the correcting term where it takes 2 times the lengths of A and B times the cosine of the angle, this internal angle between A and B. So one of the best steps that you can do for yourself is carefully labeling A, B, and C. You can use different label if that's more comfortable for you, but that's the general idea. And then identify the relative locations inside for your internal angles. Another quirky characteristic of triangles, as useful as they are, there's yet one more. It turns out that the sine of the internal angle divided by the length of the opposite leg is the same ratio no matter which pairing that you look at. So the law of sines will allow you to pick 2 pairings and have one of them be an unknown so that you can solve for that and report that for your internal angle. Once you've performed these 2 steps for your part 1 force table, you'll compare these 2 results using percent difference and percent error by comparing them to the actual setup on your table. In this situation, our experimental setup is the force table, and we're going to use that as the reference point, and now we're testing these 2 methods against each other using percent error. For your force table 2, you're going to be using the component method. The benefit that the component has that's superior to both the others is that you can add an indefinite number of vectors together and be able to get where you're going, which is to say a resultant vector for the sum of all those vectors. Well, the components come out as we did last week in that way, sines and cosines relative to which axis that we're looking for. And if we're adding, let's start with just 2. If we add 2 vectors together, well, we write down their components in this way. Now, there may be some confusion about what are these little things that say the little carrots over top of the x and y's. And the answer is this. Each vector goes in a particular direction, and we map them to x and y axes. So to help stay uniform with a vector notation, writing a vector is equal to ax and ay, we need to indicate that the length ax goes in the direction of x hat. And so x hat, y hat, and if you're working in 3 dimensions, z hat, are merely unit vectors, which means that they go exactly in the direction of one of the axes, but their length is 1. So they don't actually change anything, they just let you know the direction of that component. So we write ax in the x hat direction, ay in the y hat direction. Same thing for bx and by, they're both going in the x and y direction. And in order to add these up, we simply need to rearrange the order and get all the x hat direction going all together, all the y hat direction going in the same spot, and then we can group them up. We say ax plus bx in the x hat, and so on. So that we say, well, whatever the resultant vector is from adding these together, in this case c, corresponds to cx in the x hat direction, cy in the y hat direction, where cx is ax plus bx, cy is ay plus by. When you do yours, you'll have 3 vectors added up. You're going to compute a 4th vector, the d vector, using this process, and then you'll again compare that to your force table results and follow the rest of the calculations therein. Okay, so I do want to briefly touch on Newton's 3 laws because that's going to be up not just for this week, but also for your next lab, which will be studying Newton's 2nd law. So let's just take a quick glance at Newton's 3 laws as an overview, and we're going to focus on this week's only. So Newton's 3 laws of motion are Newton's first law, which concentrates on constant velocity, explains forces that are acting on an object that are under constant motion, whether there's 0 forces or we have to assess that all forces are acting on it, but they're balanced, much like the basketball earlier in this walkthrough. So, Newton's 2nd law says, okay, under the condition that we're undergoing constant acceleration, what is happening with the force? We'll go into more detail in the next lab. And then the Newton's 3rd law, which is kind of a consequence of the first law, says that when you have 2 objects interacting, what happens then? And again, we'll get into those at a later point. But for now, I just want to again highlight that under this situation, what you're doing today, you'll be dealing with Newton's first law. X and y axes, the forces along both directions is 0, sums net to 0, and therefore you have no net motion on your force table, and your ring is perfectly balanced around the pin. And so in this lab, you will be working with a force table that looks something like this, and it's on a stand with legs. So this is not detachable, this is just a spare that we have. But I want to direct your attention to properly reading this. Some of the older generations came out printed backwards from what we do now, so this one goes clockwise, increasing in number from 0. We want to pay attention to 0 and going counterclockwise and increasing angle. So make sure that you're careful about reading your force table that way. As you perform this experiment and you get the weights into position and with the amount of mass that you want, your aim is to get this ring to center around this pin in a nice symmetric fashion. You want to be able to pluck at the masses and give it a little bit of motion, and then it'll settle back down into this stable position. So that's the goal. You'll be working with plastic pulleys, and the important thing that I want to highlight for you is that these are plastic and they do not need to be tightened very strong, just enough to be snug in place, but no tighter than that, otherwise you risk actually breaking the pulley. So make sure that you're gentle with these when you're putting them in place and that you're adjusting them so that we're not damaging the equipment. Everything is plastic. You can adjust the angle of the pulley once you got it in place on the table, so take that into consideration to make sure that your strings are level. Each station is equipped with your force table and 4 sets of slotted weights. These slide weights should be nicely organized. You can see that there are 10 20-gram pieces, one 50-gram piece at the bottom, one 10-gram piece, and two 5-gram pieces should be in every blue bin. One thing to be careful of when you're working with these are just screwed into place, and so the 50-gram piece can be removed. We don't want to remove it, but it may be loose and can cause you some trouble. So make sure you give it a little twist to make sure it's tightened before you start loading it onto your force table. In case the assembly drops, it doesn't come apart and make a big mess for you. When you're finished, please make sure that you've reassembled all of your hangers and all the masses in the same way, and then stored them back in their place. We want to make sure that we have a nice setup for the incoming class, and also to make it easier for us to put these away at the end of this lab week. We do have protractors on hand if you don't have one of your own. Everybody should be pretty familiar with how to use these, so I'm not going to go into detail. I just want to highlight that we have that. Okay, so this is your force table, and as you can see, it's got a round table that has degree markings going all the way around. It's got a ring that's centered on a pin, and there are some other rings and strings. Not every one of them has rings sitting on a ring. Some of them, the strings are directly on the ring. So take that into account when you are making your adjustments. Now, before you begin anything, you want to make sure that your table is level so that you're not introducing a wayward force into your strings that are going across the surface here. And so you can adjust the balance by turning the knobs at the feet and using a level to make sure that it is perfectly level. And to ensure that you have gotten it to a true level, set your level parallel to each of the legs to cover the entire surface of the table and make sure it's ideally flat. So we want to place the pulleys onto the table edge once you've got it balanced. And keep in mind, these are plastic pulleys. They do not need to be super tight in order to be fixed in place. So please be careful and don't over tighten them. But we place them onto the surface in a position that we want. In this case, I want the 0 here. And remember, we have this notch that we're going to align with the markings on the table. Not too tight, just enough for this to sit put. And try and make sure that this pulley is level as you can get it. And you can confirm that when you eyeball it and make sure that it's going straight across from the pulley to the string. So you may have to drop this down just a little bit, but don't let it rest on here. And then the same thing with another randomly selected part for your second vector. So maybe B goes here, not too tight. And then you run your strings over your pulleys like so. And then you estimate the third one. This is another reason why you want to make sure that these are not too tight, is that with it lightly tightened, you can adjust it, loosen and adjust it a little bit easier as you are balancing things out. So we'll put a weight over here on B, and notice it's pulling on the ring. Put a weight over here on the second one. And we're going to adjust that to make sure that they're horizontal. And then take the third one. This is light enough. The fourth extra one is light enough that it should not make any difference on your system. So you can adjust the mass once you got it here. This is pointing more towards this way. So either I need to pull more force this way. So we'll give that a bit of a shot. And we see that it kind of jumps around there. So that angle seems to be okay. Let's lower that down, make sure that these are all even equivalent to each other. There we go. And now the question is, do I have too much weight? And you just begin adjusting your weight of your equilibrium mass until you get a good centering of that. So it's still pulling too heavy this way. Take off more. Put this back. Be careful not to drop the weights, and if you do drop the weights, that you're now it's too heavy that way. So these are 20 grams each, so it'll take some time to adjust. With it there, you can give it a little tap and let it see if it settles. Maybe you need just a millimeter or so, and that looks really centered right there. So that we line up that notch with that angle. We're measuring positive angle from 0 in the positive X direction, as it were, all the way around. Well, that does it for this week's walkthrough. I'd like to remind you that if you have any questions, I'm not just talking about the physics lab, I'm also talking about any homework questions. You're welcome to ask any one of us, myself, your TAs, obviously your classmates. And don't forget, we have the Physics Help Center that's available over at ID Weeks. And so, just a couple quick reminders, make sure that you're pushing chairs back in and you're making sure to clean up all of the weights and getting them back in the blue boxes. This week's lab is, I remind you, a worksheet lab. Make sure you check out the worksheet lab report format and follow it. It should be pretty straightforward at this point for you. And until next time, we'll see you in the laboratory. Never been able to do that before. See you later. Serious face. Hey everybody. Let's just make sure that we remember to stop recording before we disconnect devices. Hi everybody. Welcome to this week's pre-lab activity. Hi everybody, I get that every time, every week I say pre-lab activity, not walkthrough. Next week's filming is a lot shorter than this one because the video is already into place. All right, let's do it.
Why does every photographer and video maker have one of these?
Because they provide three-dimensional lighting.
Never thought of it.
Yep, there's a lot that goes into video making.
I will think about that.
The first one is algebraic. The first method is through the tip to tail. Get it wrong. Okay. The first step is adding graphically. So I'm not getting it right.